So let's start with our second example of applying the principle of impulse and momentum, principle of linear impulse and momentum. So here we've got there's a motor basically, and that's attached to a tree trunk probably, which we're trying to pull using a cable. Okay, so ab iske baare mein let's see what the particular that's our actual physical problem, and then let's see what exact physical quantities we're given. So the log is 500 kg. It rests on the ground with the coefficients of static and kinetic friction being so, and the winch delivers a towing force T to its cable at A as shown. So that is basically that this motor or winch, as it's being called right here, is going to develop a tension in the cable. Or how that tension is developing is shown by this graph right here. That as the time progresses, initially there's a quadratic increase in the tension, and then the final tension becomes constant. So what do you want to find? We want to find, okay, with this sort of a tension profile in the cable, that is, with this sort of tension being applied to the log, what's the speed of the log at t is equals to 5? After 5 seconds, what's the tension? So that is कि overall हम अपने time के profile में we're going to be somewhere here, right? 5 seconds. Okay, so let's think about this. I think first a good idea would be to find what is the static friction in this case. ताकि let's just compare does the tension ever actually exceed the friction? That is the log ever going to move or not? पहले तो ये determine कर लेते हैं ना. So as I said, we're gonna read through this problem and then we'll work from there. Read through करने से पहले लेकिन वही हम discuss कर लेते हैं अपना plan क्या होगा. So as I was saying, I think a good idea would be first to just figure out will the tension ever exceed the friction? That is, will the log ever move? So first off, we'll do that. Next, if we then establish okay, the tension does become larger, that means it will move, फिर हम उसको अपनी free body diagram या फिर impulse momentum diagram draw करके find कर लेते हैं because if you notice what the properties we are being related are, we have the time, we want to find the speed, so that is I have the time, I want to find the velocity, and of course I know the tension being applied, so I know what the force is. So please look what's happening, or chale, fine, mass B. So this is exactly the properties which are related by the principle of linear impulse and momentum. So which is why I'm just going to directly implement that one to then find the speed of the log. Note again, if you wanted to, you could do this using any of the, you could use this using the kinetic and kinematic relationships that we've done before. Okay. Right, so let's first move to determining the friction. Okay, so of course it's the static friction that we are interested in to begin with, because once that's exceeded, then the log will be able to move, right? So you guys recall friction is just the coefficient of friction multiplied by the normal force. So we first need to find the normal force. Just looking at the equation of motion, or actually the equation of equilibrium in the y direction, I can see that the normal force is just equal to the weight. So I've just got this right here. Now let's see kitni how much tension ya phir how much static friction there is. That's just mu s times n, right? So the friction, static friction turns out to be this much. 2,452 newtons. Or of course, I can already see from my graph कि वो तो at a maximum value of 6,400 जा रही थी the tension, which means कि the tension does exceed the friction and it will cause it to start to move. Okay, so now let's just figure out as well what would be the time when it starts to move. What is the time when the tension exceeds the static friction case? Or how I do that is just I input my tension being equal to the static friction to get the time, to find the time. So it seems at this time of about 2.5 seconds, somewhere here maybe, somewhere here probably. It starts to move after this. Okay, usse pehle tak it wasn't really moving, so the tension wasn't really doing any work if we take our previous concepts in consideration. Okay, so after that it starts to move, and then what I'm just going to do is directly apply the principle of impulse and momentum to see what its final velocity would be. Now just the issue is, please remember that I'm trying to find the speed at 5 seconds, right? So जो impulse being provided है, which is of interest to me, is what? It's the 5, and when it started to move, roughly 2.5 seconds. The impulse which is going to cause a change in the momentum by the tension is going to be this area under the curve. Right? So I do have to find this, and the easy thing would be for me to break this down into two sort of segments. One going from 2.5 to 4 seconds, where I'll have to integrate this equation, and the next one going from 4 to 5 seconds. Okay, so that's all that I'm going to do. I'll apply the principle of linear impulse and momentum between these. Okay, noting that the initial momentum is 0 at this time, because it only started to move here, so the momentum is going to be 0, this initial momentum, right? Or as I said, iski integration ko let's break it down into two. One is the integral of this one, so 2.476 se leke total 5 tak, but when I break it down into these two, right? One is from the initial starting time till here, and then the next one is just going to be this rectangular area, which is easy for me to find, going from 4 to 5 when the tension is constant. Please also remember that during all of this, there is the frictional force acting on it. Okay, so there is also an impulse being provided by that frictional force. Or when it's moving, that frictional force is going to be determined by the coefficient of kinetic friction. So I have to have my mu k in there. And that's just going to be a constant. So again, it's a straightforward multiplication of the frictional force multiplied by the total time duration in which it acts. Now, also remember, again, because I'm just reading through it, so मुझे अलग-अलग चीजें इधर point out करनी पड़ती हैं. Remember that impulse and momentum are vector quantities. तो जो भी ये f dt को हम integrate कर रहे हैं, उस impulse की direction वही है जो उसकी force की direction है. इसी वजह से if I've taken my positive to the right, मैंने x axis को to the right positive लिया, और मैं इधर देखी scalar in the x direction की principle of linear impulse and momentum apply कर रही हूँ. Then for that case, my tension ka impulse is positive, whereas my friction is acting in the minus x direction, so it has a negative impulse. Right? I hope that is clear to everybody. Acha, so that's it. Then we've got everything that we need. The only unknown right here is the final momentum, or the final speed, or the final velocity. And we can just directly find it by solving this through. Okay. I'm going to wait for someone to point out or ask a question. Sharjeel, do you have any questions? Yes. I'm just hoping that someone will point it out. Ali, which one? Second step. So I need this here. The second step being, is expression में right here? In which time is required to exceed, tension is required to exceed. Okay. all I was saying was कि देखें, when we draw the free body diagram of the log, it's going to have a tension acting to the right and a friction always acting to the left. So Zaira, it will only start to move when it's no longer in equilibrium. That is when this tension exceeds mu s n, right? That is when the tension exceeds the the static friction case. ठीक, तो हमने पहले सिर्फ यही किया. We've just found out कि what is the time when the tension exceeds the static friction and the log will start to move. Okay. अच्छा, इसी से मैं what I was hoping was, I think आधे लोग quiz करके जा चुके हैं. Nobody is here. I'll carry on. Okay, I talk to myself in half of my classes anyway. So, what I was interested in, I was just wondering if somebody might ask, okay, why are we taking the time limit to be from 2.5? हम 0 से क्यों नहीं कर रहे? Does anyone?
Yes, ma'am.
Yes, ma'am.
मैम वो डिस्प्लेसमेंट ही 0 है उससे पहले.
ओके, डिस्प्लेसमेंट 0. लेकिन डिस्प्लेसमेंट 0 होने से इसमें क्या फ़र्क पड़ता है? ये तो प्रिंसिपल ऑफ इम्पल्स एंड मोमेंटम है, नॉट वर्क एंड एनर्जी. तो इम्पल्स का तो ताल्लुक टाइम से है ना, तो ये फोर्स का तो टाइम जो टेंशन है वो तो 0 से अप्लाई करना है, वो तो ये पूरा इम्पल्स अप्लाई कर रहा है.
मैम लेकिन अगर कोई वेलोसिटी नहीं होगी तो चेंज इन मोमेंटम 0 होगा तो इम्पल्स भी 0 होगा.
That's not entirely true. इम्पल्स तो एक्ट कर रहा है उसके ऊपर.
मैम लेकिन अगर फॉर्मूले के हिसाब से देखें तो वेलोसिटी 0 होगी तो चेंज इन मोमेंटम 0.
चले देखें, मैं आपको अपना इसकी एक्सप्लेनेशन बताती हूँ. इसकी एक्सप्लेनेशन ये है कि इफ़ यू लुक एट इट वेरी क्लोजली फ्रॉम ये पूरे टाइम ड्यूरेशन पे, कि वो 0 से ले के 5 तक अगर हम अप्लाई करें, और दैट इज़ व्हाट द sort of more thorough approach would be. Then from 0 to 5, when I apply this, I can still see that my initial velocity is 0, so initial momentum is 0, right? But then what happens? Now let me just apply each of the, remember it's a summation of the impulses. It's a summation of the impulse. So first one I'm going to have 0 se leke 5 tak, I have my tension dt. Then I have 0 se leke 2.5 tak, what did I have? I had, ये 2.476 जो है, मैं 2.5 लिख रही हूँ उसको. I had the case of my static friction. You remember? वो भी तो थी. And then I have from my 2.5 until the end, I have my case of kinetic friction. और this was the key part, कि जो 0 से लेकर 2.5 वाला part है, उसमें तो whatever I do throughout, the static friction is going to be equal to the tension. मतलब ये कि for this time duration of 0 to 2.5, the impulse provided by the tension and the impulse provided by the static friction both cancel each other out. They balance each other. And that's why, जिस तरह मुझे अभी कोई कह रहे थे कि इसीलिए वजह से कोई change in momentum होता ही नहीं है उस duration में, 0 से लेकर 2.5 तक इस वाले duration में. Because for this part, the friction is equaling the tension. Okay? So that's why I just jumped to directly looking at the this time duration. Clear to everybody now? Okay, actually वो उसको आप include कर भी लें, so we just end up back at this.
Yes, ma'am.
ठीक है जी, thank you very much. Okay, so that's it. We solve it and we find the answer. And then after that, there's nothing, this straightforward substitution and solution of it. Yes, so this was just another example of applying the principle of impulse and momentum. So what was happening was that there was an impulse being provided by the tension and the friction as well, of course, for that same time duration. और उस impulse की वजह से there was a change in the momentum of the log. that we can then find. Note that the usefulness of ये हमने directly एक ही in one go we are able to find the final velocity. So in none of this did we have to find its acceleration और फिर उस acceleration को integrate करके फिर time निकालना and so on, because all of that is already incorporated within this principle. Perfect. Okay, so no questions in this part, yes? So that means I can move to my I can move further with my principle of impulse and momentum, where what I'm going to start to do is now to look at the principle of impulse and momentum for a system of particles. ठीक है जी. अब as before, जिस तरह हम equation of motion को भी जब system of particles के लिए consider कर रहे थे, या फिर when we were considering the principle of work and energy for a system of particles, the neat thing as before is that this is just a linear equation for each particle, and if you're finding it for an entire system, then all we have to do is that we have to sum it for all of the particles. That is, we just find the total initial momentum of each of the particles, add to it the total impulses provided to each of the particles, and then that would equal our final momentum, the sum of the final momentums of all of the particles. But again, let's go back to the fact that अगर हम एक system को consider कर रहे होते हैं, तो for each particle there are actually two types of forces acting on it. One are forces which are external to the system. मतलब ये कि वो बाहर से from the sort of the surroundings of the system they're acted upon on each of the particles. But then there are also our internal forces. मतलब ये कि इस particle के ऊपर there is going to be an internal force acted upon it because of the effect of these other particles. अब what happens is कि we all know by Newton's third law of motion that all of these forces are going to be equal and opposite to each other. ठीक है? So उसी वजह से अब when I'm summing it over the entire system, then these internal forces के impulses just cancel out. इस वाले particle के ऊपर वो internal force इस direction में act कर रही है, तो इस वाले particle के ऊपर वो ही internal force opposite direction में act कर रही होती है. And of course time duration भी हम same ही मतलब it's going to be acting for the same time duration, right, with the internal force. So the point is that it just disappears again. So the impulses caused by internal forces, they always sum to zero and they disappear. Such that when I then write my principle of linear impulse and momentum for this entire system, the only forces that feature in it are my external forces. We've already seen this before, right? You remember? We've seen this before in the equation of motion, that when we're considering the whole system, wo internal forces disappear ho jati hain. We've already also seen it for the principle of work and energy, that those जब हम पूरे system की work and energy देखते हैं या conservation of energy देखते हैं, those internal forces disappear. Perfect. So the same thing happens here for the principle of momentum as well, impulse and momentum as well. Okay. Right. I'm sorry some of my animations have disappeared. Don't need to worry about too much of the text. That's just there ताकि जब आप revise कर रहे हो, it can help you out. You just need to listen to what I'm saying. So, as was the case of we had come to a conservation of energy, a principle of conservation of energy from our principle of work and energy, और उस case में it arose when we had no non-conservative sort of work done on the system. So here as well we have this case जो मैं अभी आपको बताती हूँ, which is कि अगर हमारे पास एक system of particles के ऊपर कोई external force ना act कर रही हो, that is, there is no external impulse acted upon it, then what we end up with is just that the initial linear momentum, the sum of the initial linear momentum is equal to the final linear momentum. That is just written it this way out, it's just this, right? Okay, and now this thing is called, because look, it's what's happening. There is no change in the total momentum of the entire system, so that that's why this little statement right here is referred to as the principle of, or directly just the conservation of linear momentum. ठीक है जी. Now this is actually pretty important. Why? Because when we're looking at systems, we'll discuss some systems in between. There are actually so many cases where there are loads of internal forces, sure, but के external force उस system पे कोई नहीं होती. Such that because of the fact that internal forces के impulses तो already they disappear, then we can directly apply the principle of conservation of linear momentum for such systems. Abhi, this will become clear to you as we consider some examples of what constitutes a system exactly. Okay, again, I apologize. It seems that my what's the word? My animations have disappeared. But I'm just as I said, either actually just bear with me. मैं 2 seconds में. Okay, so what I'd been talking about was okay, we had started to look at the principle of linear impulse and momentum applied to an entire system of particles. Okay? And then we saw how the internal forces do not have any net impulse, so they disappear from the principle. And then I was discussing, consider the special case when even external forces का भी कोई impulse है ही नहीं इस system के ऊपर. That could be either because there is no external force acting on the system, or because the impulses just balance out. Okay, such that this term is 0. Then what we end up with is something known as the principle of conservation of linear momentum, where all that we've got is that the sum of the initial momentums of all of the particles will be equal to the sums of the final momentums of all of the particles, right? अब इस पे I want to discuss के ये कब what kinds of systems can this, or what kind of problems can this hold true for? Now that's the nice thing about it, which is कि कभी we can actually simplify our principle of linear impulse and momentum and actually apply it even for the case जब हमारे पास वो net impulse की term, ये वाली जो term है ना, even when it's not directly equal to 0, but it's approximately equal to 0. Now let's talk about it. कि when can that be the case? Clearly, it's a function of two things, force and the time over which it acts. So when either of these things is small enough, then the net impulse could actually be pretty small and could be ignored. Basically, I want you guys to think about a problem right here. Because this is we've thought about it before as well, but what's happening here is that we've got a hammer and it's driving into a nail. Okay? So, and we'll see shortly that for this entire system, the conservation of momentum actually holds true. Now that may seem strange to you because clearly there are large forces acting here such that ye cheez, is this going to be 0 or not? We'll see. Okay. So pehle to let's just draw out the free body diagrams of each of them separately. Okay, so pehle let me just consider ye meri nail ki free body diagram hai. So clearly that's just gonna have the weight acting downwards on it. Even agar aapne normal force bhi include karni ho, so also the normal force from the ground acting on it, and then the massive, the large force applied by the hammer. ठीक है जी. So if I now talk about each of these separately, now first of all, the problem that we're considering is for a very short time duration, right? We're only considering it for the case when F acts on the hammer, just जब वो strike होती है. So that strike is actually of a very occurs for a very short duration. So during which हमारा ये weight तो constant ही रह रहा है ना, और उसका magnitude in comparison to this massive hammer की force is pretty small. Such that in this case, क्योंकि एक force का इतना large impulse है, then I actually can consider कि इस बेचारे का जो impulse है वो तो बहुत ही छोटा होना है. कि weight का impulse compared to the large hammer force is just going to be pretty small. Okay, so when we do something like this, which is that we consider the impulse of a force to be negligible compared to other impulses, then what we call this type of a force is a non-impulsive force, as the name implies. मतलब ये कि उसका impulse इतना negligible है कि हम उसको non-impulsive consider कर लेते हैं. Whereas this force F, this is pretty large in comparison to the weight. So clearly this one is going to have a fairly significant impulse being delivered to the nail, such that this force is called an impulsive force. Okay, pretty straightforward from the names, right? Now let me at the same time look at the free body diagram of the hammer. Now for the case of the hammer, again, that's going to have a weight, its own weight, and an equal and opposite force exerted on it as it was exerting on the nail. So this will have that same large impulsive force acting on it, but in the opposite direction. लेकिन इधर भी वही चीज़ अप्लाई करती है, which is कि the weight of the hammer is pretty small compared to the force which is acting on it, this hammer force, या फिर strike का force. So which is why again the weight of the hammer is going to be considered a non-impulsive force, whereas the striking force is going to be an impulsive force. Okay. Now the point here is कि इधर तो clearly एक large किस्म की impulse input हो रही है इस force की वजह से on the nail and separately also on the hammer. So मतलब ये कि इनको अगर मैं individually देखूँ इन particles को, then clearly the conservation of momentum does not apply. Then clearly the net impulse is not zero. There is a net impulse acting on the nail and on the hammer. But instead, if I consider this to be an entire closed system, then what? Then I know that my large, sorry, इधर weights भी बने हुए हैं. Then my large impulsive forces, they are of course just internal forces in the system, right? So the net impulse because of this capital F actually cancels out when I look at both of the particles as a system, right? And at the same time, the weight side already discarded because they were non-impulsive. Their impulse was very small. Such that in this case, we do have the case where the external force ka dt is actually approximately 0. That is, F so has the impulsive force is turned into an internal force and therefore does not need to be considered. And the weights, they were non-impulsive. They had a very small impulse. They had a negligible impulse. So for this combined system of the hammer and the nail, the principle of conservation of linear momentum holds true. और यही इसी को यूज़ करके हम फाइंड कर सकते हैं एक्चुअली कि जब वो हैमर स्ट्राइक करता है और उसकी इतनी तेज़ वेलोसिटी या स्पीड से सडनली ज़ीरो हो जाती है, सो नेल की क्या स्पीड या वेलोसिटी उसकी वजह से बन जाएगी, एंड देन हाउ फार वुड इट गो इनटू द मतलब what would its be its speed after impact, and then how far would it go into the wood or the wall or whatever we're talking about.
मैम
जी प्लीज.
मैम अगर हम पूरा सिस्टम कंसीडर कर रहे हैं कि वो आइसोलेटेड है तो हैमर को भी तो हम कहीं से फोर्स दे रहे हैं ना.
हैमर को हम कहीं से फोर्स दे रहे हैं, आप उसको भी सिस्टम का हिस्सा बना लें. सो अगर मैं खड़े होके उसको दिस इज मी, मैं खड़े होके उसको मार रही हूँ, राइट? सो कंसिडर मी पार्ट ऑफ द सिस्टम. I am part of the system. Why that's important is because मेरी तो velocity को कुछ भी नहीं हुआ ना. It was 0 to begin with. It ended at 0. So my point is then in this closed system, I don't contribute anything to the momentum, the change in the momentum.
मैम लेकिन हमारे हैंड की वर्टिकल वेलोसिटी तो चेंज हुई है ना, जबकि तो हमने हैमर से नेल को अंदर करा।
तो आप और पीछे चल जाए, मेरे पूरे आप को इंक्लूड कर ले। मैं आपको यही तो कह रही हूँ। जो मेरा हाथ, the hammer was moving because of the internal forces between my arm and the hammer, and
मैम
then
हम
my
इस तरह कह
arm was
सकते हैं कि
moving.
जो हमने
My arm was moving because of the internal forces in my shoulder, and so on. The point just being that you can always go back to eliminate these large impulsive forces within some closed system,
ठीक है
such
मैम,
that
समझ आ गई कि अगर हम हैमर को पकड़ के मतलब नेल पे मार रहे हैं, तो हम अगर हैमर को जो हैंड से फोर्स लगा रहे हैं उसका रिएक्शन भी तो मिलेगा, दोनों कैंसिल हो जाएंगे।
बिल्कुल बिल्कुल, मैं यही कह रही हूँ। इसीलिए दिस
ठीक है।
थिंग अबाउट द कंजर्वेशन ऑफ लिनियर मोमेंटम इज एक्चुअली वेरी इंपॉर्टेंट, बिकॉज कहीं ना कहीं जाके यू कैन एक्चुअली कंसिडर अ सिस्टम जहाँ पे देर इज़ नो एक्सटर्नल फोर्स बीइंग अप्लाइड, राइट। इसीलिए मैं जब इनिशियली देख रही हूँ उनको अलग अलग, तो वो उनके अंदर इम्पल्सेस हैं इंडिविजुअली, बट व्हेन आई जस्ट स्टार्ट टू थिंक जूम आउट, और जिस तरह आपने कहा कि अच्छा इस पर भी तो कोई लग रही है, तो फिर मैं और जूम आउट कर लेती हूँ, आई इंक्लूड माई सेल्फ एज पार्ट ऑफ द सिस्टम। और फिर मेरे ऊपर अब आप वेट की आ कहने लगेंगे, तो वेट और नॉर्मल फोर्स भी कैंसिल हो रही है, एंड सो ऑन, such that there will be a point where you can define a closed system where there will be conservation of momentum rather than impulses acting. Does that make sense? In particular, let me help you out with this. Hanji, please.
Let's say that the nail was shockproof or something. You know, it absorbed the impulse.
Yes.
Does the conservation of linear momentum still apply, or do we have a different equation for that?
Okay. Sirat, in that case, so in that case there is going to be some sort of a recoil of the hammer, या फिर वो भी नहीं है, आप कह रही हैं वो उसी के अंदर ठा लग के वो उधर ही वो हो जाता है। I'm thinking,
Yeah, let's say there is no recoil.
जैसे सैंड के अंदर कोई चीज फेंके वो वहां पे रुक जाती है।
अच्छा, ओके, जब वो रुकती है तब भी उसके जो इनिशियल ये वाला हिस्सा होगा, राइट, वो तो डिस्प्लेस करता है ना, राइट। लेट मी रिपीट दिस। सो फॉर एग्जांपल हमारे पास जब शॉक एब्जॉर्बर्स या कोई भी चीज़ें होती है और कोई चीज़ आके उसके ऊपर इम्पैक्ट करती है, ऐसे आके लग रही है, so what happens is कि it's just when we say shock absorber, what we mean is कि उसका कोई initial portion वो उसका momentum सिर्फ change हो जाता है, या फिर वो एनर्जी को absorb कर लेता है, वो इसकी kinetic energy को absorb कर लेता है, right? So just trying to point out here कि even in this case there would be conservation of momentum because there will be a change in momentum of just this small part of it. Whereas it's not possible, at least what I'm thinking of right now, it's just not possible कि the nail remains completely unchanged, वैसा का वैसा ही, और उसके ऊपर you strike something और इसका suddenly zero हो जाए. That's just not going to be possible. There has to be some transfer of momentum, or in other words, some transfer of energy from here to here. Does that make sense?
Then, ma'am, in that case, I think we will include energy in the equation. This equation won't stay the same, right?
Sirat, so that, as you recall, I said to you that these are just equivalent ways of saying the same thing. So the principle of conservation of energy, the principle of work and energy is just another way of stating the principle of linear momentum and impulse, right? So अगर मैं उसको energy transfer के forms में देख लूँ या फिर मैं उसको momentum transfer के version में देख लूँ, I'll get the same thing at the end of it.
Okay.
Right?
Okay.
So, for example, if I look at it in terms of energy conservation, what I'll see is that the kinetic energy gets converted into stored elastic energy in these things. So whenever something gets deformed, it acts like a spring, basically. So it will store some elastic potential energy, right? So उसकी kinetic gets transferred into this. But also अगर हम momentum के version में देखें, then I'm saying कि this, sure, not the whole thing, but some parts of it are going to get some initial velocity and get displaced, basically, which is the same as saying it will get deformed. But I'll think about this even more. Okay, I will think about it.
Yeah.
Right. Okay, you guys also have a think, and we'll talk about impact and shock absorbance and how that works for in the version of the conservation of momentum. Perfect. Okay, so just saying, just how do we, what kind of systems can we say कि हम zoom out करते करते पहुंचेंगे? तो उसके लिए it's a fairly straightforward thing to consider कि these are certainly closed systems for which the conservation of momentum will hold true, which are the two particular types of systems, two particular types of problems. One is the case of when you have bodies which are अभी मैंने लिखा नहीं है actually. Oh, it's just particles collide or interact. But I do want to discuss two particular types of systems when particles are colliding or interacting. One is the case when something is exploding. ठीक, that can be considered to be a closed system क्योंकि उसकी internal forces की वजह से ही that large particle या फिर rocket जो क्या हो जाए क्या कहते हैं उसको वो disassemble होता है जब एक part दूसरे से अलग हो जाता है and so on. The internal forces cause it to become multiple particles. So this is a case of a closed system where the conservation of momentum would hold true. And the secondly also when you have a system like so, when you have bodies which are striking each other. So one body is colliding with another one, then these can also be considered to be closed systems. Two main cases of systems of particles for which the conservation of momentum holds true, basically. ठीक है जी, तो whenever we see problems like this, we can immediately see कि okay, these are just इनके आपस में there are just internal interactions such that then and there is no external applied force. या फिर in the case like so, the external applied forces have very small impulses, so I can use the principle of conservation of momentum, basically. Okay, so let me just repeat some of the things that I'd said, as always. So first of all, yes, whenever we have a large force acting even for a short duration, it is going to lead to some impulse, and hence why it's called an impulsive force. Then in that case, we have to look at our entire principle of linear impulse and momentum, not the conservation of momentum. And examples of such impulsive forces are, यही वही बात है कि even though वो short duration के लिए act कर रही होती हैं, but they're so large that they do have some impulse. अब ये होता है when we're looking at, most often when we're looking at just single particles, right? So for example, as I said, an explosion or the striking cases में, if I don't consider the entire system and I just look at one of them, as I'd done for the hammer or for the nail, or for example here when a baseball is striking a the ball is being struck by a bat, then just for the ball, it's going to have massive impulsive forces acting on it. इसी वजह से तो उसका momentum change हो जाता है for the ball, just for that one particle. But remember that when we start to look at some closed systems, such as the one for exploding or striking bodies, then these internal forces become these impulsive forces, they become internal forces such that we can eliminate their net impulses and we are only left with the conservation of momentum. Okay. Next, there are non-impulsive forces as well. Now, these are basically forces जो negligible हो, मतलब compared to some other large force. ये बहुत ज़रूरी है to note कि this is in comparison to something else, right? अब if a body just has a weight acting on it और उसी weight की वजह से वो नीचे गिर रही है, clearly that weight is an impulsive force in that case, because the weight is the one causing the change in momentum, right? I hope that makes sense to you guys. So this description of something being non-impulsive or impulsive is relative, basically. It is in comparison to a number of forces. Also note कि it's also important to define कि आपस में comparison हो रहा है forces का, but also कि the time duration has to be pretty important as well. So अगर as an example ये baseball which was being struck by a bat के बारे में देखें, और इस दफ़ा what I start to consider is not just the moment of impact that the ball had, not just this one, ये मेरा bat है और ये ball है, but instead मैं ball की पूरी trajectory को देखना चाह रही हूँ. Then clearly मेरा time, अगर मैं सिर्फ impact को देख रही होती, तब the weight would be very small compared to the striking force and I could ignore its impulse. But when I'm looking at this part, the trajectory part, then clearly the weight is the one that's important and is causing the change in momentum, and therefore it has to be considered. Okay? So just the point was to highlight that we have to be a little careful when we decide that the impulse of a force is negligible or not. Okay, and then whether we can ignore it or not. And also to remember to if you're looking at a system, फिर वो internal forces को हम eliminate कर सकते हैं या नहीं. Okay. So just these few comments, and then I have a few examples that I want to get through today. So again, easy ones we're going to read through and the difficult ones we're going to do. And then I also, the topic of angular momentum came up, so I also want to discuss that if we get a chance. Otherwise, we'll move it to next week. But let's see. So what's happening? In this example, I believe we've got a large mass M initially. Let's say कि वो कोई shotgun का, I am sorry, लेकिन I'm going to have to start using some of these terrible examples of bullets and projectiles and so on. So उसके अंदर में भी कोई spark और वो fuel या gunpowder burn किया या whatever we did, such that that initial pellet has now broken down into loads of tiny particles. Now clearly this thing itself was a closed system to begin with and is going to be a closed system at the end of it. No external forces acting on it. Consider that we are also ignoring the weight. And why I'm going to ignore the weight is because I think I'm just going to look at just the moment of explosion. ठीक है जी, so moment of explosion के अंदर I know that the weight is going to be pretty small in comparison to that exploding force. ताकि अगर मैं एक particle को देखूं खाली, तो then I can think of the weight as being a non-impulsive force. ठीक है जी. So now what do we want to do? We know the initial mass and its velocity. We know what the mass A is, what the mass B is, and what its the final velocities of VA and VB are in Cartesian coordinates. And what I want to do is I want to find the velocity of fragment C after explosion. Please note again, we are going to stick to Newtonian mechanics and non-nuclear mechanics, so to speak. So what I mean by that is that conservation of mass would also hold true. No fancy conversion of mass into energy or vice versa. So अगर मुझे MC नहीं given इधर, which I can see I don't see MC, then the mass of C is just going to be the total mass that we started with minus the two that have formed, right? So MC is just going to be 50 kg. Sorry. So, right. So that's it. And then after that, all internal forces, weights ignored, standard, straightforward conservation of linear momentum. So let's jump into it. It's too easy, this one, right? So conservation of momentum ke accordingly, the initial total momentum of the system must be equal to the final total momentum of the system. So initial momentum of the system, I just had one particle, and then after that I have my three particles with their respective velocities. So I'm not going to know what my VC is, so I'm going to have to separate it out into the three components, which I've done. And then just solving them each for the I component, the J component, and K components to find what they are. nothing complicated, right? So I think if anything is unclear in the concept, do let me know. Otherwise, I think we can. I hope we can all do the maths of it at least. ठीक? So just the key part was this is a closed system. It's a closed system before and it's a closed system after. The exploding forces are all just internal forces. Perfect. Okay. Next example. So next example we've got ये भी अक्सर काफ़ी होता है कि एक पीछे से ट्रेन आके ना आगे एक और को लगती होती है. I don't know if you guys have seen this. So very often वो it's obviously it's going to have an initial velocity and then it comes and strikes the other one and they combine together. उनका latch activate हो जाता है, so on. So what happens then to their final velocities when they're combined together, right? या फिर what is the sort of the internal force between them? Either of these things we could find out. So for example, what's happening here? We're finding the two rail cars with masses of this and velocities as shown. And we want to find the speed of the cars after they meet and they connect. And we also want to find the average impulsive force between the cars if the coupling takes place in 0.8 seconds. ठीक है. This is useful. This extra part is a little useful. So for the first part, let me just consider this to be a closed system, right? So clearly then वो जो भी force is acted upon on A by B or on B by A are internal forces, such that I can then just apply my conservation of linear momentum. Initial momentum is going to be, sum of the initial momentum is just going to be equal to the final momentum, right? So what do I have? MA was 15,000 mass times 1.5 plus 12,000 times 0.75. But please notice, again, sorry, I forgot, we should always start with the coordinate system. So such that this was a minus. Remember, momentum is a positive x direction के momentum I'm considering. Remember that momentum is a vector quantity, okay? So मैंने उसका सिर्फ x equation लिखी है, just the scalar x1, क्योंकि y में तो वो वैसे ही conserve हो रहा है, it just stays 0, the momentum stays 0, okay? And this will be equal to what? Their combined masses afterwards, which would be 27, and their final velocity. We'll find out what it is then. So what do I get? अगर आप लोग मुझसे पहले कर दें, then you can just tell me the answer, whereas I'll take ages to type things up in my calculator. Okay, anyone please, what is the final velocity? Patani, where do you guys disappear to? Where
minus 0.25.
Minus
0.5.
ये क्या हो गया? Who is this with the minus 0.25? Please check कीजिएगा. Let me check again. Or anyone else could confirm, please, if this is what they're getting.
0.5 ही आ रही है.
0.5 ही आ रही है. Or it is positive, so that means it's to the right. ठीक है जी. So ये तो easy. The first part we've done by just considering the entire system. Now, if you want to find the average impulsive force between the cars, let's have a think about that. That means कि वो तो कोई हम internal force को consider करना शुरू हो रहे हैं, है ना? तो उसके लिए हमें कोई individual A या फिर B को consider करना पड़ेगा. What I'm going to do is I'll use, चलें A. इसे A नहीं चलें A ही ठीक है. Okay, I'll use A. Okay, so now let's draw out either the free body diagram or the momentum diagram of A. Friction तो है ही नहीं, There is no friction. So in my, okay, weight downwards, normal force to the right, and then this some impulsive force, which I'm going to draw to the right positive right now, which is going to be my F average. That's it. That's all that's acting on it. So now let me apply my principle of linear momentum, linear impulse and momentum. So that is F dt is equals to m2 v2, right? So initially it has a I'm just going to write it to the right. Just give me 1 second. So F dt is just going to be F average multiplied by the time over which it's acting, 0.8, and that is going to be equal to the mass times the change in its velocity, v2, which was 1.5, and now it's moving to the right with 0.5. So 0.5 minus 1.5. So F average turns out to be what? Minus something. ऐसा ही है जी? यही आ रही है, तो गुड हो गया हमारा, and that makes sense, right? Why? Because yes, there was a decrease in its momentum. Initially it was moving to the right with a velocity of 1.5, and then after the collision it was moving to the right with a velocity of 0.5. So there was a decrease in its momentum. Or remember that, you also should remember this, that the resultant force acting on something is also the rate of change of its momentum, So clearly when there was a decrease, then this would have been a negative resultant force, that is, it was acting towards the left hand side. Yep, it was decelerating it. So many ways to say the same thing basically, as you've seen. Right. So any queries for this one, or shall we move on? Okay, no queries. Okay, so last one that I want to do, which is a little difficult example. Okay, is wale ko bhi, it's easy one. So I'll read through this and then I want to do one difficult one. Actually, you guys can read through this one. This is again something related to an explosion. A 10 kg projectile is fired from point A. Its velocity is 80 meters per second at 60 degrees initially. Initially ये थी. And the projectile explodes at its highest point B. इधर आके वो explode कर रहा है into two 5 kg fragments. One fragment moves vertically upwards at Vy this, or we want to then determine the fragment, the velocity of the other fragment immediately after the explosion. So सबसे पहले तो, what's clear to me at least, इसके हमें उसकी initial velocity ये वाली given है अगर, और उसने explosion आके इधर B पे होना है, तो what I want to do first of all is to find its velocity at B in x and y components essentially. ठीक है, क्योंकि you remember कि principle of impulse and momentum is a sorry, it's a vector equation. So हमें उसके x and y components चाहिए होते हैं whenever we're gonna apply it. So let's do that. Okay, so let's say it exploded at its highest point, which means कि वो और ऊपर नहीं जा रहा था particle, which means कि at B it had a y component which was 0. ठीक है जी. So अगर उसका y 0 था तो उससे मैं उसका x भी determine कर सकूँगी. और ये x तो हमें पहले ही पता है. This is making life, ये तो इन्होंने आसान ही कर दिया काम सारा. x we already know because it's projectile motion and we know कि vbx would have just remained a constant. You remember this, right, guys? Because it's projectile motion, the only acceleration is in the y direction. So at this point B, it has a horizontal acceleration which I can find. Let me find that. So exactly right. This is using this is just 0, or vbx is just going to be whatever its horizontal velocity was initially and that's just AD cos 60. So that I get this 40 meters per second. And then after that, I have two particles. One particle I know moves just upwards with, I think it was 12 meters per second. So I can apply that as vector form agar likhe, so that's just going to be 12J, right? So just implementing all of that in vector form, we can solve it and find our velocity of the second particle. Please note that for the second particle, we don't know what angle that velocity is going to be at. So we have to keep the magnitude and the angle that it makes with the horizontal as unknown and solve it. ठीक है जी. So once we do that, again, it's pretty straightforward. So this again wasn't too complicated. ठीक? Okay, now let me move to a complicated one. Okay. Yes, so I want all of your attention and for you guys to try to solve it as well. So we've got a toboggan. Maybe probably pronunciation galat hogi. Toboggan, I don't know. It's just a sledge basically. You know the जिस पे snow की वो लोग बैठ के करते होते हैं. So a toboggan having a mass of 10 kg starts from rest at A and carries a girl and a boy and having a mass of 40 and 45 kg respectively. So A से हमें पता है they start. When the sledge reaches the bottom of the slope at B, the boy is pushed off from the back with a horizontal velocity given right here, measured relative to the toboggan. Determine the velocity of the toboggan afterwards, neglect friction in the calculation. अच्छा, I hope कि you all might have noticed this कि जब आप पता नहीं कितने आप लोगों ने मोटरसाइकिल से किसी को गिराया होगा, लेकिन जब आपके पीछे से या साइकिल से किसी को गिराया होगा या किसी भी ऐसी चीज़ से किसी को गिराया होगा, so you might have noticed कि जब कोई गिरता है पीछे से तो आप थोड़े से आगे की तरफ और तेज़ हो जाते हैं. And that is exactly because you guys together were a closed system and because of the conservation of momentum, right? So that's exactly why you speed up when someone else behind you falls off. So that's what's happening here as well. ठीक? So let's see. Let's first what I want to do is I want to determine कि उनकी velocity थी ही क्या at B when they were combined, जब वो they were both on the sledge. Okay, so for that कैसे करें? A से B और velocity चाहिए, height हमें पता. I think I'm going to use the conservation of energy. I think that might be simpler. ठीक है जी. So first, हाँ जी.
मैम वो बॉय पीछे पुश कैसे हो रहा है?
गिर गया बस. हाँ.
किसी भी फोर्स के बगैर ही हो रहा है?
वो जो भी फोर्स होगी वो इस स्लेज के अंदर ही है, राइट? मतलब कोई एक्सटर्नल दरख्त नहीं आके लग रहा या कोई रस्सी नहीं खींच रही उन्हें एंड सो ऑन, राइट? So whatever the reason, maybe the girl just got sick of him and pushed him off. In any case, जो उन्होंने उस पे लगाई होगी वही उनके ऊपर वापस भी लगी है, right? So it was an internal force that caused him to fall off, not something external to this closed system. So from A to B, because I want to find their velocity at B, let me apply the conservation of energy because it seems to me कि मुझे कोई frictional forces है नहीं, so there are no non-conservative forces. So I can then use T1 plus V1 is equals to T2 plus V2. Okay, I'll define my datum to be here. Essay, no particular reason, such that my initial kinetic energy and potential energy are both 0. Sorry, things happening themselves. Whereas my final, my final kinetic energy is going to be half mvb squared is equal, and then there was a decrease in the potential energy from my datum. So minus mg times the decreased distance, which is 3, is equals to 0. So from this I can find, by the way, mass here cancels out, even though it was the mass of the combined mass of them, and I get that my velocity at B of the toboggan is, the toboggan and the two kids is 7.67 meters per second. That's the speed, so to speak. And please note that they are they're coming to a, shall I just say, it's not written here, but I'm going to assume that this is actually a horizontal surface. This is a flat horizontal surface, which means then this velocity is to the left, like so, horizontally to the left. ठीक है जी. अब क्या हो रहा है, now afterwards, immediately जब वो B पे पहुँचते हैं, then there is a something internally happening. समझे, explosion ही हो रहा है, right? एक किस्म का, because वो एक particle से दो बनने लगे हैं. So there's some sort of a analogy to an exploding particle here, and then I'm going to use my conservation of momentum. So in that case then, remember, for a system, it's MI VI is equals to MF VF. So let's see. Initially, they're both, it's the combined mass. So it's 40. Uh-oh, my writing tab is now lagging behind what I'm writing. So 40 plus 45, and VI was to the left. Let me consider my coordinate to be something. छोड़े परे y की ज़रूरत ही नहीं है, just के to the left मैं positive consider कर रही हूँ. Okay, just to make my life a little easier. 7.767, and then final we have that the toboggan की velocity we don't know. Toboggan or girl की velocity is going to be the same. Oh, toboggan का mass भी है. I'm sorry, I did not notice that. So this is going to become, girl has a mass of 40, so this becomes 50 kg. So then 50 V toboggan plus the velocity of plus 45, the mass of the boy, times his velocity, which is going to be VB. I don't know what VB is yet, because what I'm given actually is the boy's velocity relative to the toboggan, which means what I do know is actually, ये मुझे इधर लिखने दें अलग से.
मैम माइनस वी भी नहीं होगी?
Minus would be incorporated within it if it's there. Always remember, I don't know what it is. अगर वो opposite direction में होगी तो इसकी value के अंदर minus आना चाहिए. ठीक? So here I am given that velocity of the boy, come on, relative to the toboggan is 2 meters per second pushed off the back. और ये इधर, हाँ मैं वो ढूंढ रही थी, where is the arrow? Where is it telling me? It's moving to the right. So it's sort of like -2 आ रही है, minus direction में. Or what is VB with respect to t? That is actually VB minus VT is going to be equal to -2. So what's happened here is that I've got now two simultaneous equations which I can solve, right? So what I'm going to do is कि मैं ना इस वाले से किसका ले लूँ, VT का ले लेते हैं. चले, क्या नहीं, फाइंड क्या करना था वो ले लेते हैं. वेलोसिटी से टोबोगैन लेना है तो V boy निकाल लेते हैं फिर, ताकि हमारे पास VT आ जाए. That's going to be VT minus 2. Please be very careful about what's happening with the signs. Okay. So now I'm just going to solve it. No, why is it not writing? Uh-oh.
8.61.
Perfect. I'm getting the same thing. Please notice this is positive. So according to my sign convention, that means it's to the left. और वो क्या हुआ, पहले 7.67 थी इनकी combined और अब 8.61 हो गई. वही बात जो मैं आपसे अभी कर रही थी कि जब हम किसी को पीछे से फेंकते हुए जाते हैं कहीं आगे की तरफ जाते हुए, तो we speed up because of this conservation of linear momentum. Exactly because of this. So ऑलवेज ये ना ये इस किस्म के छोटे छोटे सैनिटी चेक्स अपने रखते रहा करें, ठीक. सो डू ट्राई टू जूम आउट ऑफ प्रॉब्लम्स एंड एज आई मेंशन लास्ट टाइम कि थिंक अबाउट देम, ताकि जब आपके पास आंसर अगर लेट्स से इससे छोटा आ रहा होता तो यू शुड हैव बीन एबल टू spot that and realize that something's gone wrong. Okay, right. So thank you, Alize. Yes, you're right as well. Right. So this looked a little bit more difficult. Again, it was a starred question, by the way. But once we got to it, it wasn't too bad, was it? Achha, right. So that's exactly what the answers were. So that's well and good. Ek aur problem hai, but I think I'm running out of time today, so I'll discuss it next time in more detail. This is even more, I find, more complicated. So I'll post up this.
मैम जो पीछे आपने VB minus VT is equal to -2 लिखा था, मैम उसका ये बता दें जो ब्लॉक में जो लिखा है.
ये वाला या फिर ये वाला ये वाला ना. Okay, basically मुझे ना what had been given in the question was what the relative velocity of the boy is with respect to the toboggan, or what had been shown from the diagram was that this relative velocity was to the right. So when it was telling me that it's 2 meters per second, it was showing that the boy's relative velocity to the toboggan was to the right. अब मैंने क्योंकि अपनी positive sign convention to the left बनाई हुई थी, that's why I had written down that the boy's relative velocity to the toboggan is -2. और फिर आगे तो I know कि the relative velocity I know कि how that works out. The relative velocity, you guys recall हमने इसके बारे में बात की थी कि it's always this b minus the t, कि boy की relative to toboggan है. So it's vb minus vt and it's then -2 as it's here. Boy की velocity relative to toboggan, hence why it's going to be the velocity of boy minus the toboggan. Okay, right. So as I was saying, there's another problem in here which is even more complicated and interesting, and we will do this one later. लेकिन ये I just want to start off describing it. Basically what's happening here कि हमारे पास एक रैम्प है और ये रैम्प के ऊपर एक ब्लॉक स्लाइड कर रहा है. And what we'll notice from our problem, अगर अब हम already इसको ज़रा अब conservation of momentum के हिसाब से zoom out हुआ हुआ सोचें तो क्या हो रहा है कि ये mass जो है that is मुझे सीरत आपके क्वेश्चन के भी इससे थोड़ा हिंट आती जा रही है, लेकिन anyway, sorry. So this mass is going to slide down, right? So as it slides down, सब कुछ रेस्ट पे था, लेकिन at the end जब A इधर पहुंचता है, it has acquired a velocity or a speed. So clearly A has a momentum. And according to our principle of conservation of momentum of a closed system, अगर ये जो इंक्रीज टोटल मोमेंटम तो कंजर्व होना है, तो अगर इनिशियली मोमेंटम 0 था तो ए का मोमेंटम टू द लेफ्ट बढ़ा है, दैट हैज़ टू बी बैलेंस्ड बाय a change in the momentum of B, or it will turn out that B will actually move to the right as A slides down it, which is very interesting to think about. Okay? Because so far we had been looking at problems in जिसमें ना the ramp is something which is fixed, so to speak. Or now let me explain कि why उस केस में ramps नहीं हिलते, or why is just the block that moves down. Because those ramps, if they're fixed, then that means कि हमारा closed system जो है ना, that's the earth, that it's fixed to the ground. Right? So it's our entire earth which acts as the system. So anything which वो A की तो velocity increase हो जाएगी और momentum increase हो जाएगा, लेकिन वो जो पूरे ground के साथ वो चीज़ लगी हुई है या चिपकी हुई है, the ground has a massive mass. So even उसका momentum increase होता है, बट उसका mass इतना large होता है कि उसकी velocity बिल्कुल ही negligible होती है. Right? So do think about these things, and we will discuss this problem in the next class, inshallah. And in the next class also, what I want to do is I will discuss with you, okay, why are we just looking at linear momentum? And somebody had brought up this question of what is the angular momentum, and we'll do all of this next time. But please note that for particles, the angular momentum is actually not part of our syllabus. I'll discuss this with you in any case. Okay? Right, guys, so have a good rest of the week and the weekend, and then see you on Tuesday. Yes. Any?
मैम मेरा क्वेश्चन है, बाकी क्लास को जाने दें, रिकॉर्डिंग स्टॉप कर दें.
Sure. So everybody else is free to go.
मैम क्वेश्चन यही है कि टेंशन फोर्स से हमारी वर्क किस तरह होगा, मुझे भी सही तरह समझ नहीं आ रही, कंफ्यूजन है थोड़ी.
क्या चीज़ अब्दुल्ला फिर से बोलिएगा.
मैम टेंशन से वर्क किस तरह डन हो रहा है. टेंशन तो खुद डिपेंडेंट होती है किसी और फोर्स पे.
Okay. No problem. ये देखें अब्दुल्ला, देखें असल में ना वर्क डन का ताल्लुक इस चीज़ से नहीं है, सो टू स्पीक, कि वो कौन सी फोर्स है जो डिस्प्लेसमेंट कॉज कर रही है. उसका ताल्लुक सिर्फ इंडिपेंडेंटली इससे है कि क्या पार्टिकल की डिस्प्लेसमेंट उस फोर्स की डायरेक्शन या मतलब का कोई कंपोनेंट है या नहीं. सो व्हाट आई मीन बाय दैट इज़ कि इसी आप कंसिडरेशन को देखें कि लेट्स सी कि एक ब्लॉक है और उसके ऊपर कोई टेंशन है यूं साथ ये टेंशन है, साथ मैं आके उसको और भी ज़्यादा ज़ोर से इस तरफ खींचना शुरू कर देती हूँ फॉर वट एवर रीज़न. ठीक है जी. और फिर साथ फ्रिक्शन भी है, और फ्रिक्शन जो है वो अब मेरे ऑपोजिट एक्ट करेगी या जो भी है. अब बात ये है कि लेट्स कंसिडर कि दिस पार्टिकल एक्चुअली एंड्स अप बीइंग डिस्प्लेस in this direction to the left by let's say S. Or to make my life easier, can I just assume that F, T, F and S are constants, just ताकि मैं ना उसका इंटेग्रल वर्जन को गायब कर सकूं. ठीक है अब्दुल्ला. तो अब देखते हैं कि क्या होएगा. अब मैं वर्क डन लिखना शुरू करूं. ठीक है, वर्क डन. So I know that work done is positive if the force and the displacement are in the same direction, and the work done is negative if the force and the displacement are in opposite directions. ठीक. या फिर think about it the other way. It's the dot product of the force and the displacement. ठीक. So अगर मैं टेंशन और इस डिस्प्लेसमेंट का लूँ ना, मैं एक एक लिखना चाहती हूँ. टेंशन है वो मल्टीप्लाई होगी -S से, फिर फ्रिक्शन है. फ्रिक्शन मैंने जिस तरफ भी बना दिया, फॉरगेट के एक्चुअली वो कहाँ है, नहीं इधर मूव कर रहा है तो फ्रिक्शन इस तरफ होनी चाहिए थी ना, सॉरी. फ्रिक्शन है. ओके, फ्रिक्शन फोर्स टू द राइट है, लेकिन डिस्प्लेसमेंट क्या है, उसके डॉट प्रोडक्ट लेंगे वो ऑपोजिट डायरेक्शन में, सो -S. और फिर आखिरी क्या फोर्स रह गई मेरी, ये जस्ट द अप्लाइड फोर्स, और इस वाली की ही डायरेक्शन में डिस्प्लेसमेंट है, सो इट्स जस्ट अ then a plus s. So now look what happened. The work done by the tension was negative, the work done by the friction was negative, and the work done by the applied force was positive. Now here's the thing, वही मैं आपको कही थी ना कि it doesn't, it's not necessary कि ये इस केस में ऐसा हो रहा है ना कि डिस्प्लेसमेंट जो है वो ओवरऑल, क्योंकि ये F ज़्यादा लार्ज थी तो इसलिए उसकी रिजल्टेंट फोर्स इज टू द लेफ्ट, दैट्स व्हाई इट गेट्स डिस्प्लेस्ड टू द लेफ्ट. लेकिन उस रिजल्टेंट फोर्स के अंदर के जो कंपोनेंट्स हैं उनमें से ये टेंशन जो थी ये तो इस अप्लाइड फोर्स के ऑपोजिट वर्क करने की कोशिश कर रही थी. दैट इज इट वाज वो तो देखे ना, डिस्प्लेसमेंट तो लेफ्ट पे हुई है, हेंस व्हाई दिस इज अ नेगेटिव वर्क डन.
मैम अगर हम बॉडी के ऊपर डायरेक्ट फोर्स लगाएं यानी कि रोप ना हो तो फिर तो टेंशन वैसे ही खत्म हो जाएगी.
फिर से बोलिएगा, बॉडी के ऊपर क्या ना लगाएं?
मैम यानी कि अगर बॉडी पे रोप के थ्रू कनेक्ट ना हो, वैसे ही हम हाथ से पकड़ के उसका फोर्स लगाएं बॉडी पे तो फिर तो टेंशन नहीं ना होगी, वो तो फिर फोर्स ही रहेगी ना.
मतलब ये कि आप कह रहे हैं,
मेरा मतलब ये कहने का मतलब ये कि टेंशन तो हमेशा डिपेंडेंट है ना किसी फोर्स के ऊपर. अगर एक्सटर्नल फोर्स ही नहीं है तो टेंशन भी नहीं होगी, तो फिर वो वर्क डन किस तरह कर रही है?
मुझे आपकी पूरी तरह बात नहीं समझ आई, लेकिन एक चीज़ थिंक अबाउट इट दिस वे कि ये टेंशन इज़ नॉट, इट्स नॉट अराइजिंग बिकॉज ऑफ दिस फोर्स. दिस टेंशन इज़ प्रॉबेबली कि उधर कोई मोटर बैठी हुई थी और वो मोटर साहब इस केबल को खींच रही है, एज वन एग्जाम्पल, राइट. या फिर ये टेंशन इज़ अराइजिंग बिकॉज कोई पुली यहाँ पे था और इधर से यूँ वेट नीचे जा रहा था और सो ऑन. द पॉइंट इज श्योर दैट टेंशन इज़ गोइंग टू बी अराइजिंग. वो तो हमेशा हर चीज़ की तरह ये फोर्स मेरे मसल से आएगी, मतलब एंड में जाते 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 आप किसी और चीज़ पे पहुँचेंगे. लेकिन द पॉइंट इज़ फॉर दिस व्हाट्स द वर्ड, दिस सॉर्ट ऑफ ऑब्जेक्ट ऑफ इंटरेस्ट, हम तो इसके ऊपर सिर्फ कंसर्न है ना. मुझे इधर कंसर्न नहीं है कि ये टेंशन आई कहाँ से थी, इस वजह से मेरा मतलब था.
मैम वो हमने जो एक एग्जांपल की थी जिसमें वो टेंशन वाले जो वर्क था सारा वो कैंसिल हो गया था, वो वाला केस क्या था?
वेरी गुड, वेरी गुड, वेरी गुड, बिल्कुल.
उसमें कंफ्यूज हो गया मैं.
वो ये केस था कि हम एक क्लोज सिस्टम को देख रहे थे. जिस तरह अब हम शुरू हुए ना, ये हम सिस्टम्स को देख रहे हैं, लाइक पूरे इधर भी. जैसे लेट मी शो यू कि जो हमारा एक्सप्लोडिंग पार्टिकल्स हैं, कहाँ गए? इन एक्सप्लोडिंग पार्टिकल के अंदर इंटरनल फोर्सेस थी कोई. अगर आप एक्चुअली एक पार्टिकल का एनालाइज करेंगे तो फिर वो फोर्सेस आर एक्सट्रीमली इंपॉर्टेंट एंड दे प्ले अ पार्ट, राइट. लेकिन when we start to think about the whole system, then it turns out that the effect of the internal forces disappears. मतलब जब हम work done on the entire system consider करें या फिर अभी जो हम momentum को consider कर रहे हैं, तो उस केस में internal forces के impulses they cancel out. और वही हो रहा था उधर के tension वाले केस में कि वो थी हमारे पास, let me show you. वो थी हमारे पास आई थिंक एक मास जो पुलिस सिस्टम था, जो कि ये इधर एक उससे लगा हुआ है, ये किससे लगा हुआ है. द पॉइंट बीइंग कि दिस टेकन टुगेदर इज़ ए क्लोज सिस्टम. इन दोनों का आपस में जो भी मोशन हो रहा है वो एक दूसरे के वेट्स से या उसकी वजह से हो रहा है, राइट. So that's why वो tension का work done, जब when I looked at the entire system includes कि जब हम summation कर रहे हैं तो I'm doing summation on T1 plus here. मतलब ये कि kinetic energies of both the particles, work done on both the particles, and then the final kinetic energies of both the particles. तो फिर it cancels out.
ठीक है मैम,
ठीक है जी, थैंक यू सो मच जी।
थैंक यू।
ओके जी, अल्लाह हाफिज़।